All right, everyone. Today we are going to be talking about power. Power. Okay, so I just want to start off by talking about the units of power, um, and as well as just how it's not necessarily how it's derived, but just breaking down the units into their various components. So going back to mass, going back to our masses, our time intervals, and so on and so forth. Because I think it's important because when we get into stuff like power and energy, we're so far away from the original units that they were based on that it's kind of hard to remember how they interrelate to one another and how we can convert between them. So, as we can see here, power is denoted by the unit watts. And a watt, let me erase that, make that W a little nicer. A watt is equal to energy, joules, divided by a unit time. And if we recall, energy, denoted by joules, we can say that joules are simply a force times over a distance. Force times a distance. And because if we remember that work is equal to force times cos theta, so the angle at which the work is taking place, times the distance, force F cos theta d. And we can go even further than this to say that force, we're going to go one step further here, force is equal to mass times acceleration. And what do we have here? What is acceleration? Well, acceleration is meters per second squared. So if we bring this all the way back to power, we can say that, okay, joules can be rewritten as equal to kilograms times meters per second squared times meters, because that would be the distance unit here. And then, so when we plug that into watts for power, we can say that power is equal to kilograms times meters squared per second squared divided by seconds. And then when we do the math, we get that power is equal to kilograms times meters squared per second cubed. Because dividing this fraction out, we'd see that we'd be multiplying by the reciprocal. So this would turn into kilograms times meters squared per second squared times 1 over s. So what we can see here is that in the most basic units, power is kilograms times meters squared per second cubed. And this is really important to understand simply because when we are considering units and we're completely lost on where we're supposed to go with the problem, when we have this basis for what something represents, what power represents, or what energy represents, we can then work to get to these units with the information we're given. If we're given a series of variables that all, when multiplied together, give us the units of power, then we can figure out how we're supposed to get there. So, for example, on a test I had recently took, it was asking me to figure out the power of a train moving at 40 meters per second squared, and it gave me units of force and velocity. So we know that force is kilograms times meters per second squared, and we know that velocity is meters per second. So when you multiply these together, you get power. So with that knowledge that power is equal to force times velocity, we could then use that information, even if we didn't know what we were trying to solve for. If we knew that we're trying to get to power and we have the information of force times velocity, if we know the basic units of each of these variables, we can then figure out how to get from one unit to the other. And that's why these most basic units, these the kilograms, the meter, the distances, the weight, masses, the time, are so important to understand. And that's why I just wanted to spend a little time going over this kind of breakdown before we get into the problems. But with that being said, let's get into the problems. Okay, so to get started here, we have 5-15A. On your electric bill, your electricity usage is likely measured in kilowatt hours. And then here's an example of an electric bill. Kilowatt hours. What physical quantity is this a measurement of? Okay, so as I was just saying, we know that watts is measured in a joules unit divided by seconds. So energy divided by time. And we know that electricity bill usage is measured in watts. So this is equal to watts. We know that electricity usage is measured in watts times time. So hours would be a time unit. So we can say, when we're plugging this all in, we can say that when we're trying to figure out the physical quantity, we can say that kilowatt hours, so kilowatts times hours, is equal to energy divided by time times a unit of time. And we can convert hours to seconds because watts is in seconds. But disregarding that, since they're both units of time, we can say that they cancel out, because if we converted hours to seconds, so we know that there's 60 seconds in a minute and then 60 minutes an hour, so 1 hour is 3,600 seconds. The units of seconds and seconds would cancel out, leaving just energy. And with that in mind, when we look at these answer choices, we see that the physical quantity for electricity usage is energy, which is why D is the answer. Now, power wouldn't be the answer, because that's the unit of watts. That's what we're starting with. That's here, kilowatts. And it's watts times hours, so we're getting rid of that time unit. So recall what I was just saying about energy. So we went from kilograms times meters squared per second cubed. When we're discussing kilowatt hours, we're going to kilograms times meters squared per second squared, which is the unit of energy. And we can break down the units of each of these other ones, but they don't come together to yield kilograms times meters squared per second squared. Force, mass times acceleration, electric charge, that's not relevant, and electric current, though, that's also not relevant. So that's why D is the answer here, simply because when we are considering the units of each of these scenarios, D is the only one that matches up with our units of kilowatts times time. And this is our only other question for the day. It's 5-15B, which says, 4 students run up the stairs at constant speeds in the times shown. Which student has the largest power? So power, energy per second, energy per time. And how are we going to measure this power? Well, we see we're given a height unit, we're given time, and we're given a mass. I'm going to erase that just because that box is not matching over that unit. So we can say that energy is being expended to go up a height. So we can say that we are converting some initial energy to potential energy. So because we are increasing our height. So recall that potential energy, so PE, is equal to mass times gravitational acceleration times height. So first, when we're trying to find power, we would have to figure out the amount of energy, that is used up over this period of time. And we're given the time unit, so we can plug in potential energy into the top unit of power and say that power equals mgh, mass times gravitational acceleration times height, divided by time. And when we plug in the units for each of these, for each of the known quantities, we can continue to say that mass is 80 in case 1, times gravitational acceleration is 9.8, times height, which is 10, divided by 10. So these two cancel out, and it's just 80 times 9.8, and just plugging this into my calculator real quick. we get um, we get 784 watts. So, the power expended, the power expended was 784 watts, and we can continue to use this for each of these different cases. So for case 2, I'm gonna abbreviate power to P equals mgh over time, and we see that it takes less time for the same amount of mass to go up the same distance, so it's still in the same scale of 10 meters, which means that we have 80 times 9.8 times a height of 10 meters still, divided by 8. So, continuing this along, 80 divided by 8 is 10, so we could just cross that out and put like a 10 over it, a small 10. 10 times 10 is 100, times 9.8 is equal to 980 watts. So right now, number 2 is in the lead for most power, having the largest power. But we'll continue along with the next one. So we have power is equal to mgh over time. Now we see that mass has decreased, but time is equal to the time scenario in part B. So when we plug everything in, you get 64 times 9.8 times 10, because it's still 10 meters, over 8 seconds. We can simplify this to just 8, because 64 divided by 8 is 8. 8 times 9.8 times 10, so 8 times 9.8 times 10 is equal to 784. It equals 784 watts. So we know that case 1 and case 3 have the same amount of power. And now, considering this last scenario, we have a larger distance over a larger amount of time with 80 kilograms. So when we plug all this in, power is equal to mgh over time, and time is in seconds. And we see that 80 kilograms times 9.8 meters per second squared times, now, instead of 10 meters, it's 20 meters, divided by 25 seconds. 25. And when we plug all of this in, so 80 times 9.8 times 20, that's equal to 15,680 over 25. And when we divide this number by 25, we get 627.2 watts. And when we compare all of these scenarios, we see that case number 2 has the highest power. And we showed that through our use of the power equation. And that is why B is the answer here. So that's the last question we have for this section. Thank you so much for watching. Hopefully you enjoyed. If you did, please leave a like on the video, and have a great day.